Turning up the heat on electrons reveals an elusive physics phenomenon. When things heat up, spinning electrons go their separate ways. Warming one end of a strip of platinum shuttles electrons around according to their spin, a quantum property that makes them behave as if they are whirling around. Known as the spin-Nernst effect, the newly detected phenomenon was the only one in a cadre of related spin effects that hadn't previously been spotted, researchers report online September 11 in Nature Materials. The last missing piece in the puzzle was spin-Nernst, and that's why we set out to search for this, says study co-author Sebastian Gonen, a physicist at the Technical University of Dresden in Germany. The effect and its brethren, with names like the spin-Hall effect, the spin-Seebeck effect and the spin-Peltier effect, allow scientists to create flows of electron spins, or spin currents. Such research could lead to smaller and more efficient electronic gadgets that use electrons' spins to store and transmit information instead of electric charge, a technique known as spintronics. In the spin-Nernst effect, named after Nobel laureate chemist Walther Nernst, heating one end of a metal causes electrons to flow toward the other end, bouncing around inside the material as they go. Within certain materials, that bouncing has a preferred direction. Electrons with spins pointing up, as if twirling counterclockwise, go to the right, and electrons with spins pointing down, as if twirling clockwise, go to the left, creating an overall spin current. Although the effect had been predicted, no one had yet observed it. Finding evidence of the effect required disentangling it from other heat and charge-related effects that occur in materials. To do so, the researchers coupled the platinum to a layer of a magnetic insulator, a material known as yttrium iron garnet. Then, they altered the direction of the insulator's magnetization, which changed whether the spin current could flow through the insulator. That change slightly altered a voltage measured along the strip of platinum. The scientists measured how this voltage changed with the direction of the magnetization to isolate the fingerprints of the spin-Nernst effect. The measurement was a tour de force. The measurement was ridiculously hard, says physicist Joseph Harrimans of Ohio State University in Columbus, who was not involved with the research. The effect could help scientists to better understand materials that may be useful for building spintronic devices, he says. It's really a new set of eyes on the physics of what's going on inside these devices. A relative of the spin-Nernst effect called the spin-Hall effect is much studied for its potential use in spintronic devices. In the spin-Hall effect, an electric field pushes electrons through a material, and the particles veer off to the left and right depending on their spin. The spin-Nernst effect relies on the same basic physics, but uses heat instead of an electric field to get the particles moving. It's a beautiful experiment. It shows very nicely the spin-Nernst effect, says physicist Greg Fuchs of Cornell University. It beautifully unifies our understanding of the interrelation between charge, heat and spin transport.